All right, what's up? We're here for 6.6.
Welcome to
6.6 if you're Greene County, 7.6 if you're with the Falcons.
Again, go ahead and label this in your notes. The title of this section is Calorimetry, which we've kind of already talked about. So tell me about what does this look like?
You know, that looks an awful like that. An awful lot like that word calorie.
Calorie, which deals with heat, and meter, if you're familiar with your Latin.
Like a metry, like measuring something?
So this is like measuring. So basically, we are measuring heat, and which is something we already did in an experiment earlier.
With that metal capacity.
And you guys did it as well. So, thermochemical equations, we are going to be using the same ones, but I want you to learn a new definition here. This is called heat of combustion. And so if that just sounds like combustion means...
Combustion, when we produce energy and we burn.
We burn stuff, right? So if there's any heat that's given off, that is called the heat of combustion, and it's actually called the heat of a combustion reaction. Sometimes you'll hear me say delta H reaction, which means the heat given off or absorbed by
and
reaction.
That delta is change.
So remind me, if a reaction is endothermic, the value of delta H goes on the left side. And if it's endothermic, that means energy is flowing into or is being absorbed in the reaction.
Which means it's got a positive sign.
So this is a positive sign, positive delta H. Which means if it's exothermic, it's exiting the system, it's leaving, so it has a negative delta H, and it goes on the
right side.
On the right side. A review. So what is calorimetry?
So we already said that calorimetry was the measure of heat, but more specifically, it is the accurate and precise measurement of heat change for physical and chemical processes.
I was just seeing if we had. So what it looks like and what chemists use and scientists use most of the time is they have some sort of cup right here, and on the outside of the cup they've got water. Okay? So that water is going to detect any temperature changes going on in the reaction.
Because anything lost by whatever we're reacting is going to be absorbed by the water.
So we'll have our reaction mixture inside, and you'll see we have a thermometer going down and something that's going to stir so the reaction goes completely. And when this reaction is taking place, it's either going to give off heat,
and the temperature is going to rise.
And the water temperature is going to rise, or it's going to be absorbing the heat.
And the water temperature is going to drop.
And whatever the drop is, we've already seen we can use our Q equals MCAT equation, and that can show us how much heat was drawn in or how much heat was released.
Now let's do a check for understanding.
Okay.
Using the words systems and surroundings, so that's back a couple of videos, right? Explain why an endothermic reaction would have water decrease in heat.
Explain why,
the water would decrease in temperature.
Would have a decrease in water temperature. And I imagine you're saying when it's exo,
why does it increase?
An increase in temperature.
So this is sort of taking everything together and explaining it.
So enthalpy, when you hear enthalpy, I just want you to think of heat. This is how much heat is built in, energy is in the sample or in the reaction when it starts. And the delta H, the heat of reaction, or the change in heat, what we're going to be using is Q equals MCAT, which you're already familiar with. So when we kind of say change in heat and Q, they're somewhat interchangeable. Q talks about flow of heat and change of heat. So
how to calculate that guy?
How to calculate it. We're going to be looking, first of all, here are the units, the amount of energy that's given off per mole.
So kilojoules, joules measuring the heat, moles being per specific amount.
And we'll be using this equation. So let's go ahead and do an experiment.
Yeah.
Hey guys, so what we're doing right now is we're going to find the heat of reaction for magnesium and hydrochloric acid. So some of you have not learned yet, but this is the limiting reactant, basically meaning all of this is going to be used up before all of the hydrochloric acid is going to be used up. So we're going to first mass this, and we put it on the scale, and it says 0.3 grams. We're going to assume it's pretty close to that. So then we're going to take our insulated container here, and we're going to pour some 1 molar HCl. And just going to eyeball it enough so all the magnesium gets reacted. And hopefully that's enough. We'll see. Okay. I'm going to take an initial temperature reading of my hydrochloric acid. And let it simmer. And it looks like my initial temperature, we'll say 22.3. So TI is 22.3 degrees C. We need to know TF. And our mass of magnesium was 0.3 grams. So here we go. I'm going to drop it in. And the fizzing actually means hydrogen gas is being released right now, so we don't want to smell this stuff. And we're going to watch the temperature, and you can see, careful, it is climbing. So this is heat is being released. So what type of reaction is that?
It's exothermic.
It's exothermic. Now it's really getting going.
So heat is still climbing.
So I'm going to react this until all of my, that stinks. All of my magnesium is reacted. So until it stops fizzing, basically. And we're at 36 degrees Celsius now. Now this is getting pretty hot. 38 degrees Celsius. I can actually feel the vapors. It is getting quite hot. Let's see. We're almost to 40 degrees Celsius. We'll keep going until all of the hydrogen, all of the magnesium gas, magnesium metal is reacted, and all the hydrogen gas, it's done fizzing. So we'll know the reaction is done when it's done fizzing.
Now this is hotter than your body temperature right now.
Yeah, so we're over 100 degrees Fahrenheit. Still going.
I don't know if you can see, but I can see the vapors. I don't know if my camera can catch them.
Almost done. Watching the temperature. Can still hear a little bit. We're almost there. 44. Go ahead and say 44 degrees Celsius, and you can see if you look in here, almost all of the magnesium has been reacted. There's nothing left, nothing fizzing left in there. So we'll say 44 degrees Celsius. So this was extremely exothermic, and I know that because of the heat that was given off. Now, if this got colder, that meant heat was being taken into the system from the surroundings. But now we know heat is being released. So we actually, what is the sign of our delta H going to be?
Let's go ahead and we're going to be negative.
We are going to assume it's going to be negative because heat was being released. So let's go ahead and do the calculation.
All right, so let's go ahead and think about what equation we're going to use that uses all of these things. I've got a change in T, so I know I should have a delta T somewhere. I've got a mass, so I know I should have an M somewhere. I'm calculating my heat change, so I should have a Q. That looks an awful like my Q equals MCAT, so I'm going to go ahead and fill that in.
This is my specific heat capacity. So last time we did this, if you remember, think back to when we did the metal lab. We were having metal losing heat, and the heat was being absorbed by the water. So we were calculating Q for the water. What we're doing now is we actually calculated the temperature change in the reaction. So this is going to be our heat of reaction, or the heat released.
So we are solving for Q.
Okay, so let's look at what do we have. Well, I have two masses. I'm going to have to decide what mass I'm going to use first.
Right.
We're just going to give you this one. What mass we're going to be using is we're going to be using the mass of hydrochloric acid. And the reason is because we want to know, we were taking the temperature, right? And we were taking the temperature of the liquid.
Yep.
Well, the liquid was hydrochloric acid. So that's the reason why we want to use that mass.
And we can use a C for it because it's, long story short, kind of like water.
Yeah, and it's so we're going to actually use the heat capacity of water because hydrochloric acid is like really, really dissolved. It's really, really watered down, right? So if you have Kool-Aid, think of Kool-Aid, and you put some mix in your drink, It's Kool-Aid, but it's mostly water.
A little water bottle versus a giant water bottle of Kool-Aid.
Right. So let's go ahead and calculate the heat. We've got Q, and we're going to use our mass, which was
50 grams.
50 grams. And do we remember our heat capacity for water?
4.18.
4.18. That'll come up a lot. And I'm a little bit confused. What does delta T mean?
Delta T means the final minus the initial.
That's right. So it's T final, your final state, minus T initial. So T final, I've got 44 degrees Celsius minus 22.3 degrees Celsius. So this is going to give me my heat, my heat evolved, or the amount of heat that was given off. And if we do this, get my calculator here, I get 400, about 4,600. I'm going to go ahead and assume that. I get 4,600, and this is in joules, because grams cancels with grams, Celsius cancels with Celsius. And remember, heat is always in joules. So even if I don't know how to do the canceling, I know heat is in joules. So 4,600 joules. Now, this depends. I mean, don't you think the temperature would have gone up had I used more magnesium? If I put more magnesium, it would have taken longer to react, and the temperature would have gone up. So I've got to do something here. I've got to figure out how much energy is released depending on how much magnesium I use.
We kind of did a problem like this in our last video, so I think we could probably use that method again.
Yeah. So if we've got 0.3 grams, I want to know how many moles of magnesium that is. So if I've got given is 0.3 grams of magnesium, and my target is to find moles of magnesium, I see that I'm going from grams to moles. So if I'm going from grams to moles, what do I need to use?
I gotta use my mole map.
I gotta use my mole map, and if I look at my mole map, I see mass to moles tells me to use the molar mass, or the gram formula mass, whatever we call it.
If I'm going 2 moles, I've got to divide it.
That's right. So I'm going to start with my given, 0.3 grams of magnesium, and I'm going to divide by my molar mass. And if I look at my periodic table,
it's 24.3,
I believe.
Something like that?
Yeah. And that's equal to 1 mole of magnesium. You remember, I just got this from the periodic table, my PT. And I do that math, 0.3 divided by 24.3, and I get 0.0123. So this is 0.0123 mole of magnesium. Okay, so for just this much moles of magnesium, I ended up getting 4,600 joules. Wow. And now remember, what's our units for delta H? Delta H is
kilojoules per mole.
So what I'm going to do is I'm going to get this into kilojoules. If I want to, let's see if I can squeeze this in here. Remember, I want to divide 1,000 joules. So all I'm doing right now is converting to kilojoules. So I'm just going to move the decimal 3 times. This is going to be 4.6 kilojoules. So that's how much energy was released. And this is how many moles.
Yeah.
Well, my units are normally kilojoules per mole. So I'm just going to take this and I'm going to divide.
Because per means divide.
So it's going to be divided by 0.00123.
Are there 2 zeros?
Mole. There's 1 0. Thank you. And I know that's tough to read. It says 4.6 divided by...
We'll practice this more in class.
Give me that. So it's going to be 4.6 divided by 0.0123. And I get 374. I'm going to just loop it up here. This will be my final answer. So for my delta H, or heat of reaction,
or your enthalpy,
or my Q, Q, I get 374 kilojoules per mole.
And then we actually went online and looked at the real heat of reaction.
I think it was like 442.
Yep. So we're actually fairly close.
Pretty close, but there's something wrong here.
What's wrong?
There's something wrong with our answer, and your calculator gave it to you. You see it. So remind me, when you felt the container at the end,
it was warm.
It was warm, which means what energy was absorbed or released?
I don't know. What do you think? It was released.
It was released, yes. So since the temperature went higher, energy is released, which means energy is exiting, so it is a exothermic reaction. What's the sign of delta H?
Negative.
It's negative, so this actually needs to be negative.
Don't
300
forget that.
centimeters
No disappearing negative
per
signs.
mole. Okay. Have a good one.